Okay, so I can talk about the last. I'll talk about some stuff with the last homework, and then we can go back and start like at the beginning, if you want, if that's good. Or will it? Maybe we could start the last quiz after that stuff because we didn't. There's a lot more equations there. So well, okay, I'll just say real quick. Yeah, the pointing vector is this. I don't believe you have to know what it is. I'm going to write B. I'll tell you why in a second. It's like, I don't know. C? I don't remember. There's a number here. Mm-hmm. This, I don't think it really matters what it is at all. I mean, I'll tell you what it is. It's for a photon, okay, or a light wave. Light waves are made of, they're not by themselves anything, right? They're made of two fields oscillating, the electric field and magnetic field. Mm-hmm. E is for electric field. B is usually for magnetic field, although there's a bunch of other things. H is called the magnetization field or something like that. It doesn't matter. So it's just related by like a meter or something. Anyway, and then if you do it the right way, you can get units of speed or something like that. Anyway, the point of it is that S, where the pointing vector is pointed, that's not why it's called that. It's called pointing because I'll write it, because it's named after someone named Poynting. But it's actually really helpful because it's literally points in the direction that the light is going in. I mean, it's points in so like if you have, this is in 3 dimensions obviously, so if you have E cross B, if E is oscillating this way, the electric field, and the magnetic field is oscillating this way, the cross product has to be perpendicular to both of them. Anytime you take cross product of 2 vectors, you get something perpendicular. And so that means that the pointing vector is sort of in the forward direction of the oscillation, but that's literally the place it's going. So the only reason that you need it for like the things that we're talking about is if you're talking about like the flux, like you want to say, like if you had some kind of target here, and you wanted to, and the light had a pointing vector that was going this way, then you know that all of the light is sort of perpendicular to the surface, and so you can kind of compute if you know the intensity going down, then you can compute things with that. So I can talk about flux too. Mm-hmm. So this just tells you the direction, basically. And the magnitude tells you other stuff that we're not going to talk about right now. But the flux is going to be, I'll call it flux. I believe it's actually called flux, which is in units of, watts per meter squared. Okay, and so watts is joules per second. This is really in joules per meter squared times seconds. Okay, and so from this, and now this is where it's basically you're saying like units. Mm-hmm. You kind of just have to use the units. Like you can come up with equations, but the equations are essentially putting the units together. So this just says that that a certain amount of energy. So in terms of things like light, right? Light is like the sun or whatever. If you want to find the actual amount of energy that a surface gets from sunlight or something like that, well, every second you're just getting more and more energy, and if you double the area you're detecting, you're getting double the sunlight. So it doesn't make sense to talk about the energy of the sunlight, right? It makes sense to talk about the energy in, let's say, 1 square meter for every second, but that's literally what this is. So in basically, you could say the flux. So you could say if you wanted to talk about the energy of something, the energy of sunlight, you would have to say, well, how big are you capturing the energy in? Let's say this is times 1 square meter over 1 second. I meant to put the dot here, right? That would give you an actual amount of energy that's fixed, given actually it's fixed given that the sunlight is coming perpendicular. So of course, if you're at the equator, you could do, there would be a whole thing. In Boston, it would never get to this part, so you'd have to worry about a cosine. But anyway, that's all things we don't worry about. But the point is that it only makes sense to measure like amounts of photons and all that stuff. It only makes sense to talk about the energy if you tell me how big you're detecting over and how long you're measuring the thing over. So the thing that's constant is the flux, right? Energy is not constant if you change any of these variables. If you say I'm doubling the time, you should get double the energy. So you would say per second, how much joules per meter squared do I get? And per meter squared, if I measure it for 1 second, how much energy do I get? So that's this. So if you want, you could say this is an equation that says energy is flux, which I don't want to give a variable name to, times area times time. You could, now this is like, you could make this an equation if you want. I wouldn't try to like memorize this because they could give you a slightly different type of flux or something. I don't know. They could like you could vary this slightly and you'd have to worry. You know, this in other words, what I'm saying is this equation is less useful than just the units of this because you can kind of already get to it. And also they could give you something else. Like they could give you like just joules per meter squared, and they'd say, okay, I turned a light on for 1 second and it has this much joules per meter squared. Then you might be a little confused because there's no time in there. But you could use it with units. You would just say, well, I just multiply by whatever my area is and find the energy. Or if I have the energy, I could solve for the area or something like that. Mm-hmm. So essentially, what I think you should do, what I think you should be able to do from all this, is go from this statement, which they would tell you. If they tell you it's in joules, they probably won't even say flux. If they just tell you something in this units, you should be able to get to this equation. And then solve for whatever not just solve for E, but you could solve for, if you're given E, you could solve for something else. So like in one of the homework questions, I think you had to solve for time, and you were given the total energy and the flux in the area or something like that. Mm-hmm. Another thing to keep in mind, so I just graded your homework. Another thing to keep in mind is that I didn't really care about the exponentials very much, like at E to the, something times 10 to the minus 7 or whatever. I didn't care about those very much because it's easy to be off by a lot, but a lot of people were off by a lot. And one of the things that I think people did was it said like an area of 1 nanometer squared, and you had to convert this to meters squared. So this is, I guess I'll write it here. So 1 nanometer is 10 to the minus 9 meters. Is that right?
Yes.
Yeah. And so 1 square nanometer is 1 square nanometer is 10 to the minus 18 square meters. Okay, so I think some people just forgot that. People were off by a factor of 10 to the 9, so which is like a billion. Which when you say it like that, it sounds really, but it's, I don't anticipate this is a serious, like, you're not going to get insane points off on a test for that, but just make sure you know that, or centimeters squared, like 1 centimeter squared is 10 to the minus 4 meters squared. Because it's just like, how many centimeters fit in a meter? Well, it's 100, right? But how many square centimeters fit in a square meter? Well, now you can make a 100 by 100 grid, and now it's 100 squared, which is 10,000 or whatever. So, anyway. The other thing, too, with energy is that joules and electron volts are obviously not the same unit. Hopefully you've gathered that by now. But I think it seems in the homework they just start talking. Oh, actually, no, they do tell you the conversion. So they're both the units of energy. Electron volts are much, much smaller than joules. I don't remember the factor. I don't know, it doesn't matter. But they're different units. So there was a few people that I think did the whole thing in joules and then just wrote electron volts at the end. So they were off by 10 to the 19th, which again is a lot, but it's not a big deal. But anyway, so you can, for the most part, unless they tell you what units to use, you can use any units you want. But of course, they have to agree. So in a few of the questions, they told you the energy in electron volts and the flux in watts per meter squared, which now the tricky part here is that you had to, and that's actually, if you saw the video, you saw me pausing for about a full minute because I was like, I don't understand how you can do this. But then I realized that, watts is actually joules per second. So that's why it has joules in it. Generally, when they give you the flux in watts and some other energy in electron volts, well, it's 100% true that you will have to convert one of them. If you would want to check, so if you're doing a test, hypothetically, if anyone does a test, then you could do both if you'd like and check, make sure you should get obviously identically the same time answers. For example, if they're in seconds, if you convert this to electron volts, the seconds is still here, and you could do this. So anyway, so if you wanted to check, you could do it both ways. What else? Yeah, that's pretty much it. There was some questions on the homework too about it was like it was like energy per. You had something where you got energy per photon. Well, it was okay. Here, you got something like you had to find the energy of one photon, so you used like something like this, and you got some energy value. This is where labels are kind of useful. You don't normally have to label all of your things, right? But in this case, you might want to write that number in energy, that's some number, as energy per photon, because later they ask you that you solve something else and you get energy over time or something like that. And then later you could find now the photons per time, like photons per second. So I guess I should write energy per second. I'm mixing my labels and the units. But anyway, so now you could find photons per second by just dividing these. So how would you divide them? Well, if you want energy to cancel, you have to put them in a fraction. You want energy to cancel, but if you put this above this, you'll get seconds per photon, which you could do as well if you just have to take the inverse. Or you could put this above this one. So you take energy per second divided by energy per photon, and you divide it, you get photons per second. So it's the same. I mean, so this problem conceptually is much easier if you just think, if you go the other way, where you think, well, if I know the energy per photon, I know how many photons per second I have. I just multiply them to get the total energy. So you could also do it that way and just undo it. So these things have units, and the units, it's not, I mean, it's the units of this, when you find the energy of a photon, you don't normally have, it just has units of joules. But it's helpful to label it as energy per photon sometimes, because it's, in this case, you have other energies in the problem. So labeling things is very useful. I hope I'm not saying anything like obvious and silly, but these are all, I'm just trying to say things you might not normally do. Normally you'd write an energy and you just get a joules or electron volts, but you might want to write for one photon, because the whole point of the question, of this question I made up, is how many photons, like that. So, all right, does anybody have any questions about any of these types of problems?
I guess that's a no.
Okay. All right, what do you want to do now? We can talk about so what was I forgot what the last quiz was about, but we could talk about everything that was on the last quiz.
Waves.
Wave, that's right.
Harmonic, damped harmonic, German harmonic. That's where I get confused with all the F's.
Yes, yeah.
And when you use C versus F.
C versus F. What's C?
Yeah.
It's a great question.
Oh,
Yeah.
the
Answer.
speed of light?
Yeah, but I believe in that chapter they use C as velocity interchangeably.
You use C as velocity. Perhaps. If they're... I mean, so it is the velocity of waves of light, speed of light. But, okay. Actually, let me just see what's on the thing. Waves and strings, harmonic waves,
So,
yeah.
I have a
equation-
paper if that helps.
Oh, that's all right. I have it on here.
So that equation uses C, but that's for just normal waves. That doesn't have to.
Oh, yeah.
That's where you.
That is irritating. Yeah, okay. That is irritating. Yeah, okay. Can I take it to that?
Yeah.
All right, so I'll just write a bunch of these on the board and then we can talk about them. So this is for omega over k, which is 2 pi, right, 2 pi f, which is just this. This is 2 pi over lambda. This is lambda f. Yeah. And then they also have lambda over t, which is the same as that. Yeah. Oh, and then yeah. Here's what I wanted. The standing waves for it's like this is. I'll just write V for now. Okay. All right. Okay, I'll just put it here. Yeah, so these are some equations that are in the book. I don't like the C at all, but I guess we'll live with it. C, I guess, is the wave velocity. So I guess this should be C as well. But I'll talk about this in a second. So these are just relations. So these are the confusing parts of all these variables. Like the confusing part of this is not the conceptually confusing part like waves. But this is just because they're defining all these variables that you see like once, and it's very hard to see what it means because there's way too many things. So, so we have this. All right. Anyway, so this here says this. So I'll start with this one. Okay, I'll start with these, which is this too. This is just the wavelength, right? So these have all these waves involve this equation, real part. I'll write it as in the imaginary form, but so this is what the wave equation actually looks like. Forget about phase. Don't worry about it. But they have they're one-dimensional waves, which means they depend on two dimensions in a confusing way. But they depend on space, as in they exist over space, and they depend on time because they oscillate in time. Okay. In high energy physics, you'd call this a two-dimensional wave, but let's just not get distracted. But anyway, so these are one-dimensional because they oscillate. They exist. It's like a string, where the string length is the x dimension. So we know the total length is x equals L, and we could do some boundary things and find the harmonics. So actually, we'll do that in a minute. I'll redraw it so I don't forget. 0 at L, and this is the x direction. But then we'll get back to this later. So, yeah. So this is the wavelength over space, and this is the period, which is the total amount of time in seconds, right? So wavelength, remember, is in meters. This is in seconds. This number of seconds before the wave, if you just fixed a point in space and you watch the wave go up and down. I mean, these are all, this looks like a cosine or a sine, right? Right. So it doesn't do anything sort of crazy. So if you pick a point in space and you just watch that point go up and down, when does it return to its original position? It's going to be taking some number of seconds. That's the period. And if you watched if you froze it at a point in time, so it stopped moving, you just watched, you just traced it so it would look like that or something, and you measured the distance in space that it returns to its original position, that would be the wavelength. So that's sort of the conceptual picture basis of these things. You probably already knew all that stuff. But now if we take this and we just divide them, well, this is in meters, this is in seconds. I guess it's not totally obvious that anything of that form gives you a speed, but it does. And this would be the speed of the wave, and we just call it the speed of the wave. That's not the transverse speed of particles or anything like that, right? The transverse speed of particles is another speed, which is the speed vertically. So if our wave is given by y of x and t is, whatever, well, it's something like this, right? Whatever, I'll just say cosine kx minus omega t, whatever. I'm not really going to do this, but if we wanted to find the transverse velocity, so the transverse velocity would be the actual speed of individual particles. So now we're considering the string or whatever object it is as an actual string of particles. Those particles move only up and down. So it's like on the ocean. I mean, it's a little different. It's a little more complicated. But roughly on the ocean, if you go to like this open area, not like the beach or whatever, if a wave goes through, the individual water molecule, if you put something on the water, it'll just go up and then it'll go down and then it'll go back to normal. It won't move forward, right? No matter is moving forward. So when you have a wave like this, and let's say it's infinite, so these are all infinite because we didn't specify the boundary or anything like that. So they're infinite waves or whatever on an infinite string, I guess. And they're moving left and right and they're oscillating all this stuff. But each particle is only moving vertically. And if you actually want to find the velocity that something's moving vertically, which is not an incredibly interesting thing to do, but they ask you about it, would be the time derivative in the y direction. So it'd be dy dt. Remember, y is the vertical direction. This is x, and then time is not shown. Oh, sorry, so that dy dt. So it'd be the time derivative, because the velocity is always a time derivative of the y directions. This will tell you the speed that it's moving vertically in y. And if we do that and we apply it to a specific point, we should be able to get the answer. So that would be this is the transverse velocity. Of a particle. They would probably cite the word particle when they ask you about it, because so these are about particles. Now, when we talk about these quantities, we're no longer talking about particles, right? When we talk about like the length that you have to go to return to original, you're now talking about the actual wave as like a mathematical form. And this is the speed that the wave is moving. This is the speed the wave is moving in the, depending on the sign here, the x or the positive or negative x direction. So this is the actual wave moving. Again, no matter is moving forward in the x direction at all. Yeah, it's a little, well, okay, anyway. And yeah, so this is, so these things are all properties of waves, right? They're not properties of particles on waves, that even though that's how they're made. Anyway, okay, so then this will be the frequency. Of course, this is just 1 over the period. And again, you can see it has the right units. So now we go to this, and this is still the same as the velocity of the wave, but now let's say we want to write it, now if we just sort of move to the left here, of course, this is the same as this, like it's just, if we multiply by 2 pi over 2 pi, which is 1, and then we put the lambda on the denominator of the denominator. This is just an algebraic thing you could do. Now, you wouldn't ever want to do this unless you knew that there was something that was going to lead to, which is that we have these properties of waves, we have these variables, but none of them are in the actual equation for a wave. So we have an equation for a wave, but like these have nothing to do with these, it seems, right? How do they relate? Well, this is basically the source of all the complication, is the fact that when we put things in exponential, they have to be angular and have units of radians. But when we want to actually measure things, like if you see a picture of a wave, you don't want to do anything in radians, right? You just want to actually measure the wavelength. And those are actually, these are the things that, when we talk about photons, we talk about wavelengths and all stuff. We don't talk about radians, because who cares? So this is all the confusion, essentially, is the relation between things with radians and things with that are sort of obvious, sort of mathematical, obvious to see with a picture. So if we just do this algebraic identity, where we just do this is identical, that we multiply by 1, essentially, then we can say this whole top, 2 pi f, is going to be called omega. So remember, f had units of hertz, which is 1 second, 1 over seconds. 2 pi is always 2 pi is always radians per cycle, right? That's like the label that 2 pi always has. Why would you use 2 pi unless you meant that? And so 2 pi radians per cycle times, and now frequency is really cycles per second. And so we get, this has units of radians per second, which makes sense, that's what we want. So we multiply 2 pi radians per cycle times f cycles per second, also called hertz. And then we get omega radians per second. Now this has the right units to just directly multiply time in any trig function we want. So anything that looks like this. If we put something in a cosine, it can't have any units. That's just, it has to use a radian, sorry. And if we put a time here, well, the other thing here must be a 1 over time type thing. Really, it must be radians per second, right? So we know that it has that same formula, so we can put it here, and that's exactly what we have here. And the denominator is a little more tricky, because we don't normally see like just cosine of kx by itself. That's not, you could totally have that. It would be identical. The thing in the inside has to use units of radians. This has units of meters, so this must have units of radians per meter, which is exactly what k is. It's just we don't. It's sort of like it's a frequency, right? But it's a frequency over space, which is a little bit sort of strange to imagine. But it's just like over time you have some frequency in basically how many. It's like every second, how many radians do you go through in your sort of propagation, your evolution on the wave? This is just saying every meter, how many radians do you go through? So all this relation between, so time and space here in these wave equations are treated identically. There's units for both. There's units that compare radians to each one. They're sort of very symmetric. So it's just that we don't normally think of them as the same, so they don't normally ask you the same type of questions about them, but they're treated exactly the same. We don't really have a unit for 1 over lambda. If we did, we could just put it right here. But that's not. I don't really care. We could. I think it would be called a wave number or something. Actually, they might call this a wave number. Sometimes they call it a wave vector if it's a vector.
They call it a wave number.
They do k, like the magnitude.
Yeah.
Okay, so 1 over lambda is, I don't know, nothing. Something, a spatial frequency, I guess you could call it. Anyway, we don't need it, so we don't need any more variables. But basically, that's the only reason why it looks different is because we don't have a name for that missing variable, but that's fine. So, so those are all those variables. Again, the whole point of why we're introducing so many is because we have two ways of looking at waves. Well, we have one way of looking at waves, which is a way that it's very obvious what the period and the wavelength is, and the other way, which is the mathematical formula for waves, doesn't have that in here at all. Now, we could actually write, you could only use these variables, we could actually only use these two variables and write the equations for waves just in terms of those. We would just have 2 pi's all over. Like we would have like 2 pi, 2 pi over lambda times x or something. Plus, anyway, it would look really messy. So that's literally the only reason, is so we don't have 2 pi's literally written in here. Does that make sense? Okay. So that's all wave variables that describe waves. When you actually have waves on that are from a source that you know about, like these are things like you could find the speed of the wave if you knew properties about the wave. But what if you just knew like there got to be some other way to find the speed of a wave, like based on what's making the wave, right? Like what's the actual forces involved or something. And it turns out that the sort of standard example that is going to be used 90% of the time is a string with fixed ends where there's some tension on it, right? So it's a string with some length, and it has fixed ends, it has some tension, and it has some mass density mu. And then through some, there's a derivation I think in the book that's a little dry probably, that you could find the speed of a wave due to a string with tension and mass density mu. Looks like that, it's the square root of t over mu. So now, luckily, we have 2 completely different ways to look at these waves. We could say what's causing the waves, the forces, whatever, this is external things you could do. But then, of course, this is equal to lambda f, just, So we can so this, actually, this relation here, I know I probably just made it more confusing, but you know what I mean. The fact that these 2 are equal, doesn't even matter that they're equal to velocity, who cares? But they're equal to the same thing. Is actually really cool because this side is entirely things that you can control externally. This is like for a guitar or whatever, you could change the tension, right? And you can change what string, how big it is, whatever, something like that. Anyway, so and then this will tell you things that you hear, right? These are things you hear and external things. So the important part is that when you hear it, it's because the string is actually oscillating. And when the string oscillates at some frequency f, if the string oscillates at some frequency f, it vibrates the air at that same frequency as you hear it. So the sound you hear is the same as I know it's kind of obvious, but I just want to make sure everyone knows it. The sound that you hear is the same frequency as this way it's oscillating. That's how all musical instruments work.
So your mu is mass density.
Mu is mass density. So yeah, so mu is the total mass over the total length of the string.
Okay. I think they use rho sometimes.
Yes. So yeah, sorry, I should have used rho. This is this is in the lab class that I teach. Yes, you can also use rho, but rho is more general because rho usually means density of anything. over its dimension, essentially. Actually, yeah. If you're using tension here, you have to use linear mass density. Okay, meaning something over L, right? You can't use like if you were going to use actual three-dimensional density, like rho is mass over volume. Okay, that would be like the density of a gas or whatever. You'd have to use, I guess, like it'd be the pressure or something here. Yeah, I think it'd be the pressure.
Bulk modulus?
Yeah, then you could convert it to bulk modulus over something.
Over,
You can't do it over. Oh, what's the units of bulk modulus? Is it
I think
Force over area.
force over area?
Yeah, that's pressure. Yeah, pressure.
Yes. Oh, okay. Then yes. You're right. You could use bulk modulus over rho. That would be the right. So it's the same derivation. It's just in 3 dimensions or something like that.
which we almost needed in the second quiz, but he gave us enough that we didn't.
Okay.
But it would have been a possible problem for question 2.
Okay.
Is mu. So that's just like, for example, like kilograms over like meters squared. So it's mass over volume, like the actual unit, or is it different?
For mu, if it was like a string,
Yes.
and you had the tension. Now tension is one dimensional, so you have to have a one dimensional here. It would be like kilograms per meter.
Okay.
So if you knew the total weight, the total weight or the total length or something, you could solve for the other one if you wanted. It would be the total length of the string would be down here. If they told you the bulk modulus of whatever the like steel or whatever, right? Then you could find the total density here. It would be like a cylinder or whatever. You have the cross sectional area. Of course, the volume. Then so if they told you it was like made of a certain material, and they told you the bulk modulus, then you would have C and it'd be B bulk modulus of steel or whatever over the density rho, but the density rho would now be the total mass over the cross sectional area times the length. I'm just making up these, Don't write these down without context because I don't. This just means the cross sectional. So it would just be the volume of a string of a cylinder with whatever you solve for it.
Random question. Are you recording this?
Yes.
Okay.
You
So
decided you don't want to say something that you were going to say?
I plead the fifth.
Okay. Yes, I am recording this.
Thank you.
I hope I'm recording this. Yes. I'll record Mondays too. I'll try to put it up on Monday night. I usually can, but sometimes my internet is really slow. Okay, does that make sense? Well, I can talk about harmonics now.
Sure.
Is that oh, I thought that was a no.
Oh no. Kind of like.
Yeah, so harmonics are basically continuing on this picture. I will need to erase some stuff, so. Okay, if I erase.
On the video.
It's recorded anyway. Okay. So, and we will need that equation, but I'll just write it without boxes. I don't understand why this isn't just like
That's horrible.
a whiteboard, like a normal. Anyway.
Someone knocking.
Oh, I did. That was me. Sorry. Yeah. Anyway, because the regular markers don't erase very well at all, and apparently these don't either. Anyway, okay. So now we have, let's say we have a string. Actually. So if we have, this is closed, I guess you call it. I don't know if they'll actually say that. But it just, like if it's like a string, anything with vibrating a string, it's closed loop. What this means is the boundary conditions. So it just means that the ends have to be closed. Closed means, sorry, I'm not
So
saying
like
anything
finite.
useful. Finite, but yes, okay, these are all finite. So I could have something that's open. And what open means is, would be when this close means that the end points of the string have to have 0 amplitude. Okay? So now remember when we talked about just general waves, they just moved all over the place. There were no points that were fixed. Right? That was just the e to the whatever. I'll write it now in the trig form, which is just the real part or whatever. Cosine of kx. Actually, I'll write it as sine because, well, you'll see. I'll write it as sine of kx minus omega t. Okay? This is y is whatever. Okay? Now, in general, those move all over the place, and there's no points that are just fixed for all time. There's no nodes, right? Nodes are points where the amplitude is 0 at all times. Of course, there's an amplitude here too. So they can't describe standing waves, but as we saw with the, where do we see it? There was some video I did, I remember. Well, anyway, there was something where if you add two waves together that have the same velocity moving in opposite directions, you can get standing waves, and we can actually find what they should look like by saying, okay, well, actually, we don't need time for this, I just realized. Well, no, we don't. The reason is because these are all the properties we're going to say now are actually true over all time. So we actually don't want to include it because we want basically this to be a node as it evolves over all time. If we find the sort of shape it makes at one point in time, we know it just oscillates up and down. We know how standing waves work. So the time component we can ignore for now. We know that, let's say we know that this is position 0 and this is position L. This is the length L, a string of length L. We want L to be a node as well. And we want 0 to... Now, the reason I picked sine, now really, you could do this. So remember, one of the forms of going from an exponential to a trig thing is this. So remember, there was the way where you could just put it all in a cosine with a phase, and there was a way you could put it all... I guess I would say, and then there was this way. Okay, so this is just an easier way to see that we know that at position 0, at x equals 0, we want the amplitude to be 0 always, right? Always, that doesn't mean anything anymore because there's no time. But anyway, that means that, well, cosine at x equals 0 is 1, right? So we know that this component is always going to give a contribution of 1 at 0, so we can't have it at all. B has to be 0. Does that make sense? So what I did is just say, I'm applying these called boundary conditions. And actually, I should write them out. Boundary conditions are y of 0. Now, this is the x coordinate. At x equals, there's no time anymore. X equals 0 has to be 0, and y at L has to be 0 as well, because that's here. Now, plugging in this one, we see that, well, let me just write it all out. I'm trying to skip steps, which I shouldn't do. So we get y of 0 is, well, this gives 0, so that's fine. Then we get b times 1, so just b. But therefore, this has to be 0. So we literally automatically get, this is a 1. I really should just write b. This is how you'd write it. You get b times cosine of 0, which is 1. I'm trying to go back and do this a little more reasonably. So therefore, we literally get b equals 0. We don't have to the way I said it before was sort of making a bit of a jump. But this is literally, we just plugged in the first condition, and we automatically get b equals 0. Now we can plug in the second condition, but of course we don't even need to include this term anymore because we know b equals 0. So we have y at L is a sine kl. And there's no b.
Why are you using x and y interchangeably?
I'm not. So so x is the coordinate, is the parameter. It's like y is a function of x.
Oh.
Y is this vertical. Yeah. So once we get the function y of x, we'll get the actual shape of the wave.
Okay.
Yeah. Yeah, so okay, good. So y of L, so this is y at x equals L. Yeah, it is a little confusing because when we do multiple dimension waves, y will be a coordinate too. So I appreciate the confusion. So y at x equals L is this. Now this is 0 by definition, or by our boundary conditions. And so what does this be? Well, a, we can divide everything by a, and that's fine. We don't have to worry about issues when it's 0. So we get sine of KL equals 0. So what is this? Now this has multiple, what we're trying to do, by the way, is solving for k. Because k is the only thing in his equation we don't know. Okay, and you might just say, well, who cares? Why don't we normally just write k, and that's fine. But in this case, there's some relation between k and L. There must be, because this isn't always true, right? This could be just any number, right? And so when is sine of something equal to 0? That's when that something is a multiple of pi, right? You might have to think about that for a minute, so don't, or write that down on your sheet, because sometimes it's very easy to forget which things make it 0. So, but for sine is 0 only at n times pi for an integer n. Right? Cosine is 0 at
Pi over 2, multiples of pi over 2.
n pi over. Sorry, it's n. It's n. No.
Would it have multiple solutions? Because it'd be pi over 2 and then whatever 270 is.
Yeah. So I want to write so for cosine, theta equals 0. Is theta is, and we want to write pi over 2, 3 pi over 2, 5 pi over 2, etc. So this is going to be, it's actually going to be 2n plus 1 over 2 pi. So this looks weird. Let me write it like this. So the reason I'm writing like this is because n times pi over 2 would give you, at n equals 2, would give you pi, and cosine of pi is not 0. So we can't use so it's just this shifted a little bit, but this 2n plus 1 for any n gives you an odd number. That's just a little trick. Remember, we use that for the Taylor series, right? For stuff we use 2n plus 1 always gives you just odd numbers. 2n, of course, gives you, so actually it's the same as this. If we just say sine is 0 when on the even numbers, which are 2n, pi over 2, then we get n pi, so it's the same thing. But this, of course, we have to use the shifted by. You could think of it as shifted by 1 to give you odd numbers, or you could think of it as, if you distribute it, shifted by pi over 2, because that's how the shift of cosine to sine goes. So anyway, these are the zeros of those two functions. So I'll erase this. And so now we have KL equals n pi. Remember, n is an integer. Of course, there's infinitely many solutions, because if n is any integer, this is satisfied. And now we can actually solve for the only unknown here is k. So we could do k equals n pi over L. So we have some thing for k. And so now if we plug it back in, well, we found two things. We found that b equals 0 and that k is this. So if we go back to our wave equation and we plug these in, we get y is a sine n pi x over L. I'll make that n look not like a pi. Okay. Yeah. So now, again, we have multiple solutions, but these solutions are going to work differently. Remember, it's not like here, if we plug in any n, we get the same condition. So they seem identical. But of course, this, you can see that it's not going to give you the same sine equation if we put a different n in there. So let's start with n equals, well, if we start with, the obvious one would be n equals 0, which just gives 0, and that's kind of boring. The important part, though, is that it actually does solve the wave equation. The wave equation is solved for the wave 0. It's just not interesting. if we put n equals 1, we get what? Well, it's sine of pi x over L, and if you just sort of graph it, you can see that that's this. Now remember, our condition originally, this condition here, just said that 0 and L, x equals 0 and x equals L, had to be nodes, right? And so you might think the first one, the lowest, the longest wavelength one, I guess, it's a little bit weird, awkward way to say it, but would be the one where the first node that even appears is at L, right? There's no nodes in the middle, right? Those are going to be the higher ones. So it's, in other words, we're not like wasting any, the wave is not wasting any time in the middle oscillating. It literally, this is these, you couldn't make it any bigger without just making it 0, right? Because the first node is the first condition we have. But of course, there's many other waves, like this one, that have nodes at 0 and L. They just have other nodes in the middle too. So this would be n equals 1, this would be n equals 2, and then we could have this one, n equals 3. Now remember, these are, we didn't talk about time, but these are oscillating up and down. So they're really, it's not just this, it's like oscillating up and down like that, and this is oscillating like that, and this is oscillating like that, etc. And we could have lower and lower wavelengths. And now if we knew that the velocity of the wave, I guess I should use c, is t over mu. So if we knew fixed t over mu, let's say it was some value, then we would get f, this is f lambda. And now the wavelength is what? Well, it depends on which one we have here, right? The wavelength of this one, right? So the wavelength has an index n because it depends on this, and it's something like related to L, of course, because that's the fixed value here. So lambda n is lambda 1. Let's just write like this. Lambda 1 is going to be 2L, right? Because the wavelength of this one is going to be double whatever L is. Lambda 2 is going to be just L. Lambda 3 is going to be 2/3 of L. If you do lambda 4 is going to be L over 2. So this is a little weird looking. How did I write this last time? It's like n.
It's like 2L over n, right?
Yes, 2L over n. Yes, that's right. Okay. Yes. So you can see how, yeah, that makes sense because 2L is actually, well, okay, I was gonna say, well, you could just see if 2L is n lambda, that's actually not really that much easier to see, but it is true. You know, for n equals 2, well, 2L is over here is n, which is 2 times lambda, because it's 2 wavelengths. Anyway, that's not, I guess, easier to see at all. But anyway, if you write out the first terms, you can see it's this. And now we could find f of n. So n, again, it's, of course, has to be dependent on n because this is constant. And so I'm going to call this, I'll just leave it as c. I'm not going to write t and mu. So we get this is Cn over 2L, right? So if I write it like that, you see that n remember is an integer. You can only have values of 1, 2, 3, 4, 5, 0. And this is actually the most important part for like music, because this says that multiples, there's a constant. This is a constant for a given wave. If you fix the t, you fix the mu, and you fix the length, then there's some what's called the fundamental frequency, which is just this value because n is 1. The fundamental frequency, and then every other frequency that can be produced by the same string is just a multiple of that fundamental frequency. And then in music, you call those octaves. So to play anything that differs from another note by not an octave, you need another string. Assuming you're not going to change the. So that's why piano. Anyway, it's the whole thing. But how pianos work. Because in pianos, you don't change the lengths of the strings and stuff. And I don't. The reason I don't want to use guitars is because you literally do change the lengths with your fingers, because you add nodes, right? But for pianos, you don't change the lengths. There's just a bunch of strings already. And so when you play different octaves, of course they are actually playing different strings, but you could hypothetically you could have a 12 note, 12 note piano, and somehow if you could get it to only do certain multiples of like certain n values, you could get it to play all notes. Whatever.
Anybody want to try a problem using a standing wave? So, somebody asked about standing waves, was it?
We should probably have a problem. I agree with that.
Yeah, like we'll see on the test. So number 7-9 is a standing wave problem. It was also worked in class, and 7-10 is very similar to what we had in the test.
Okay,
Quiz. Would you like those?
sure. I can use this one, so you can keep that. This is in the back of 7.
Page 128.
7, 9. Is that what you
I think it's using the stuff you just walked.
Yeah.
Derived.
Yeah, so if y equals, I don't remember, was this in the homework? Looks familiar.
Might have been.
So
Probably it's probably right.
he would probably give you things.
I'm not good at
this. Sine 18
This isn't my own.
IT. This is the third harmonic, so you know it's n equals 3, of a standing wave where t is 250 newtons. What is the speed of the wave on the rope? So it's c. And what is the mass m? Yeah. Okay. So this has a form of it has the form of a wave that we don't see very often. It's actually, if you want to see why, you can write, you probably don't want to see, but if you did want to see why, you could write a standing wave just like this. You could look up the video where I talk about beats. Remember where there's a derivation in the book where they derive the beats and how you can write two interfering waves as just two single waves of two different frequencies. This is the same exact derivation. It's just that you put, instead of two beats being two frequencies, now you have a space and time, you separate them. But it's the same exact derivation, just so you know. Anyway, so what they're asking us is the speed of the wave. Now we know the speed is, let's just look at what we know about speeds. Well, it's t over mu. We're given t, but we're not given mu, and they actually ask us for m, so we of course know that that's probably not going to be that easy, and we don't know any other information about this. So we have to use the other thing it's equal to, which is lambda f. All right. So if this is the third harmonic, they don't tell us the length either. That's the other thing too, which, fair enough. So we know it's over some. We can draw it if we want. So it's the third harmonic. This is L. Looks like that. You know that lambda is 2L over 3 if we had L, which we don't. So if this is the third harmonic, then we can use this spatial component, right? This is going to be kx, right? So so this implies that k is pi over 2, right? K of, let's say, 3.
Should we write down the general equation for two standing waves interfering? It's the 2d sine kx times cosine omega t minus pi over 2. Or you can make it sine omega t.
Sorry, two regular waves interfering?
Two identical waves
Yeah.
interfering. Should we write that down and then use it to pull it out?
I think it's actually easier than that because.
Okay.
Well, okay, yeah, okay. So there's two ways you could do this. One is you could actually convert. One is you could convert it to the form of a standard standing wave, which is this, which is like the exponential, and then you could write it as like sine of, kx plus or minus omega t. But I think you could do. This is what I think you could do it a little simpler than that because I think you can just directly take these things. So this would imply that if an omega of 3 is 18. What?
Equation
Oh, sorry,
7.21.
Oh, yeah.
And then you just take out the phase, and you can just do sine omega t.
Yes.
Which is exactly what he has there. And then you pull out the 18 pi and the pi over 2, and that's your k and your omega.
Yes. Oh, yes. If you want to get to the yeah. Yeah. So sorry. Thank you. That's a way to get from here to here. Yeah, it's written in the book. Yeah. Sorry, I'm just trying to. There was a thing I did. It's probably on video. That there was a thing I did. It's yeah, I guess it's. I just feel uncomfortable at this 18 pi. I feel like it should be 9.
We'll just divide it by 2 later when we get to the equation for length.
Yeah. Okay. Anyway, okay. So and now we know that the okay. So what do we want to find? We want to find this is T over M over L. So I'll put M here, and then it's over L, so I can put it here. And this is equal to lambda F, as we said. So at some point we do need L because we do need to find M here. And of course, once we have C, we can do that. And so that would be these two. So we can use these. So the problem right now is to take these two pieces of information that are in here and convert it to lambda and F. So remember everything that was written on the board before about the difference between lambda. I don't remember this is the way to do it.
C equals omega over k, right?
Yeah,
So that's our first question, right?
that's why I'm bothered because I thought there was something else you needed to do. Yeah, okay. Okay.
Quacks like a duck.
I'm like
Looks like a duck.
99. Yeah. For some reason I thought there was some trick to converting these to these, and there was something that I got wrong the first time, but maybe this was not the same question. Okay, let's pretend this is how you do it. So I believe it is how you do it, though. So this would be, so omega, there are 3, of course, but because they're the same, I mean, they have to be the same by some relations that are up here, but because they're the same, of course, it's going to be just the correct speed. And there's going to be 36. Oh, okay, I remember 36. Okay, I guess it was fine. I guess I did it the wrong way before. So, of course, what I was thinking is somehow we could convert this to the wavelength. Oh, we could still do that, though. Anyway, okay. I'm losing my mind a little bit. So the speed is going to be 36 meters per second. I think they told us.
Well, that's in radians, right?
No, this should not be, because these are both in radians, so they should cancel. Yeah. Okay. Well, if x is in meters and t is in seconds, then yes, it is in meters per second. And so we get 36 meters per second. That is this. And now we need to find either lambda or f, right? Because of course, so now we have c. To get m, though, we're gonna need to find. Right, here's where it is. So now it looks like, we could just say this is t over mu, and it looks like we could just say 36 squared is 36 squared times mu is t, and we have t, right? So we could take t over 36 squared is mu, but now we have mu, but we don't have m. So we literally need the length. That's the actual last piece we need. So this is just a better way to say what I was writing up here. So now this is m over L. So now we just need L to multiply this. So now this is where we have to look back at. We know that lambda of, I'm erase this. So we know that, I'll erase this too.
Why would we need L if we already know what T is?
We know what T is, so this is T over mu, right? And this is equal to this. We're going to solve for mu. We can solve for mu.
Mm-hmm.
But mu is actually equal, they asked us about m.
Okay.
Yeah, sorry, I should write, this is an m, not a mu.
Okay. Sorry, I thought that was mu.
Yeah, no, it's all right. So we know that lambda, the wavelength of 3, is 2L over 3, right? And lambda of 3, we know is related to K of 3 by what? Well, lambda is in, this is where I always forget, lambda is in meters per cycle. And then, so what is it? It's like 2 pi over K, right? So this is radians per cycle, always. And this is in cycles per meter. So this, radians per meter. And so this is in, okay. So there we go. And so we get, this is all 3. It doesn't, they're all in 3, but it doesn't matter. So this would be 4, right? Meters. Is that right? And we get L is 6. Yeah, 2 pi over 2 should be 4. Yeah, so this is lambda 3, and then we plug it back in here, and we get L is 6 meters. And then we could plug that in here, and we get the mass like that. All right. Is everyone not phased by my discomfort with this? The reason I was confused is because the last time I did a bunch of this stuff first, and that was why. We didn't actually ever need to even find the frequency, which I think I did in the last time. That's why I was.
Needed it for K.
Was that?
Needed it for K, right?
The frequency, like F, I mean.
You never needed the F frequency. You needed the omega frequency.
Yeah, okay, yeah. Right, I was thinking we needed to do this, but. Right, we just kind of skipped that by staying with that. Right, we used, really I should write, we used this. So the way we got this wavelength back here, we actually could have done this, instead of this step, we could have done this one and gone through the frequency to get the length, because if L is in here too. So if we used omega, which is 18 pi, and we converted it to, omega is like what, 2 pi f or something, right? And we so divided this by 2 pi, we would get 9, and then that's where the 9 is from. And f would be 9, and then we could plug that in here, and hopefully that would work out. 36 over, well, yeah, times 3, anyway, whatever. Something, hopefully we would get 6. 36 times 3 divided by 6 is, oh, I'm doing it backwards. Anyway, hopefully we should get the same thing.
So 7/4 is one where we change the guitar's frequency by changing the tension, and then 7/10 is figuring out a standing wave, 2 waves that jump on top of each other. I don't know if people think either of those are interesting. I think he did the guitar string one in class, but he didn't put it on the quiz. I don't know if that, just a guess. I think you just have to come up with the ratios of the tension over densities. what folks have in mind. There's the beat frequency problem too. He didn't give us one of those.
Oh yeah.
And he did hit us with the reflected pressure waves. So maybe I don't know if anybody has any intuition. If he hit it with us on the quiz, I mean it's not on the final. You know, we should do the stuff that wasn't. I don't know. Or should we expect to do the same stuff that was on the quiz? I can't gauge it.
Like we
What?
Can I see the quiz? I've never actually seen the quiz.
Well, here's the
So-
quiz. And so he didn't do a change the frequency, like, you know, tighten up the string and change the frequency, and he didn't do a beat. Those are the two he didn't do. You think beats?
I can talk about beats.
So we have a beats problem. Let's see if I can find it. I think it might be. I think it might be a problem in the chapter. More this way.
No, I think it's over here.
Yes.
Yeah, because this
Is that it?
reflection.
No.
No. Okay. There's a picture. I'll look. There should be a picture. Yeah, there's.
Yeah. Question 7-4.
Yeah.
What's that? Oh yeah, and it's kind of worked through here.
Mm-hmm.
Is that right?
When Ron was done with those questions, I have another one from quiz one. That kind of
Okay.
covers the same, like,
Yeah, we can.
are we gonna cover the same shit
Right.
we've already done or like new stuff? So
Doesn't sound
maybe
like
we
you
should
have any
just probably
intuition
go over
into
all
that.
the quiz
I have
problems.
not. I can talk about beats if you'd like.
Maybe quickly.
Because I mean, the thing is that
What?
Ashley already has a pair of beats.
I was
so
distracted,
we need to go
so I
over
didn't-
sorry.
We
I was
propose,
distracted, so I
Liam.
can't.
Yeah.
I don't have. I wear my gear, but I don't listen to anything.
actually, let me see the thing is I can't really imagine a question about beats that's not just like the standard.
Yeah.
Here's two frequencies. I mean, I guess they could ask you, here's the beat frequency, what's the other frequency?
Well, I feel like it's
Told
the
you
problem
one.
where they give you two frequencies
Yeah.
and
you
they
can find
say
the-
go find the beat frequency.
Yeah. I mean, so you could remember what it is, which is probably not how they want you to do it. Essentially, it comes down to omega 1, omega 2. It's a change of variables. So that's what the. Okay. It's a change of variables from any two numbers that you write. You can write it, and I want to make sure I get the. There's these two variables too. So this is literally just any two numbers you write, even though they're the same. You could write it. So we have y is two waves. If they write with signs. No, they don't. Okay, so this is two waves, y1 and y2, right? With two frequencies. And the whole problem of beats, this whole problem is literally just saying that because any linear combination of waves a wave is something that solves the wave equation, right? Any linear combination of things that solve the wave equation also solve the wave equation, and therefore can be written as a single wave. That's the whole thing. So because of the properties of differential equations, and also the fact that if you play two sounds at the same time, I think I said this some other time, but because if you play two sounds at the same time, what do you hear? You hear one tone, right? If you don't hear two things at the same time, your eardrum doesn't vibrate in two places at once, right? It vibrates in one pattern, and it would be the sum of these two, but again, because it's a wave, it solves the wave equation, we can write it as a single wave. So that's the whole point of this problem, of the beat problem. And not, you could do this with any waves too, but it's just only interesting really here because you get something kind of weird, which is, and it's hard to see, now here it's hard to see, but if we rewrite omega 1 as omega average plus delta omega, and omega 2 as omega average minus delta omega. Now, what is this? This omega average is omega 1 plus omega 2 over 2, right? It's just the average of them. And delta omega is half of the difference. So all we're doing is saying, if we have a spectrum, this is spectrum of frequencies, and we have omega 1 here and omega 2 here, all we're doing is saying that omega average is in the middle here, and this distance is delta omega. So omega 1 is clearly just omega average. Oh, I did it backwards. That. Omega 1 is clearly delta average omega plus delta omega, and omega 2 is average omega minus delta omega. Right, so that's all we're doing. Now, the reason we're doing this is because then both of these variables have a common factor in them, and that'll be really useful. So now if we write I, let me fill this in. Sorry, okay, that's good. T plus e to the I average minus delta omega t. So does everyone get this change of variables? It's the reason it's a change of variables is because we had 2 variables at the beginning that define this, and now we still have 2. So we didn't like make up. It's not more confusing now. It's just different variables. It's not more, there's not more information, basically, is what I mean. Now, if they gave us the 2, we would still basically have to write all this anyway. So, we could just find the number, but whatever. So now we can, there's a common factor. E to the I omega bar t is common in both of these, so we could write this as e to the I omega bar t times e to the I delta omega t plus e to the minus I delta omega t. Right? And now this thing is, I guess I would write this on your sheet because it's very difficult to derive this. Actually, it's not that difficult to derive this, but you should still write it because it's easy to forget. This is actually equal to cosine of delta omega t. The reason is because it's 2 cosine. And the reason is because this is cosine delta omega t plus I sine delta omega t, right? And this is cosine delta omega t minus I sine delta omega t, and then you get 2. Here's another thing is that, remember, these, I didn't write amplitudes here, but they could have amplitudes. They should have the same amplitude, otherwise it's not really a beat anymore. It's something sort of weird. But if this was a minus sign, all that means is that they're sort of out of phase. Now that shouldn't affect anything. And if we look, you might think, okay, so we know that in principle, we know it shouldn't affect anything. If you just make one of them negative, it just means it's 180 degrees out of phase. But if we look through here, you might get worried that, well, then there would be a minus sign here. What happens? Well, if we put a minus sign here, we see that this would be minus, this would be plus again, and we get that the signs add, and we get something with a sign in it. So we get basically the same oscillation. At the end, when we take the real part, it's just going to be a phase difference. So we can see that sort of that all works. So this, and this still comes down. We didn't do anything with this. And now, this is equal, now if we take the real part at the end, we get cosine of, we get 2 all times 2 of cosine of omega bar t times cosine of delta omega t. And now this function here this is the picture that's probably in the book, that is like, so remember, let's go back to so if these were very close together, that's usually when we talk about beats, when they're very close together. So if omega 1 and omega 2 are very close, that means that omega bar is a large number, like let's say they're in hundreds of hertz or whatever, right? But delta omega is going to be very small, right? So this usually, delta omega is very small compared to omega bar. But nothing in here requires that. We didn't make any assumptions. We didn't cross out anything that was, we didn't assume anything. So it doesn't have to be true, but usually that's the case. And if that's the case, then that means that this is a very fast oscillation, right? This is very big. This is very big. So that means that this cosine of delta omega t is a very quick oscillation. It's actually very similar to omega 1 and omega 2. It's very similar to if the waves were on their own, right? It just has the average frequency. But then that means that if this is very small, this is a very low frequency oscillation. It's very long. And so we get periods. That means that if we multiply these two together, it just means that we can sort of treat it as like it's this wave bounded by this wave, right? Like I normally say with the cosine goes from -1 to 1, but if you multiply it by a function, then it goes from whatever the max and min of this function is. So if we draw this cosine of omega t, then we get like that. So that's supposed to be a very long frequency. And then this omega bar, so now we're drawing the actual function. It would be like, well, this is like plus or minus, so. Anyway, just pretend that that's, you know what I mean? So, in other words, what you hear, the tone you hear is going to be this very, very fast moving wave, which is this one, so you'll hear the average frequency. That makes sense. If it plays, 400 hertz and 500 hertz, you'll hear 450, but you'll hear it get quiet and loud periodically. And the quiet and loud will be, this is a horrible picture, but there was one in the book that's much better. The quiet and loud will be at a frequency of delta omega, the difference between them. So if you, if they were, like, let's say 1 hertz. Now these are of course omegas, so they're not,
The amplitude, you didn't carry the amplitude through, because it would be like a 2A.
Yeah, it would be, if these were both
If
A.
they were the same, it would be A, and then you'd have a 2A.
Right, it would be A throughout, and you get 2A here.
So the amplitude, so in terms of what he's going to ask for what's the amplitude, he's going to ask for what's the tone frequency, what's the beat frequency.
Yeah.
So
this is the tone.
Amplitude is 2A,
yes.
the tone is omega bar, the beat is delta omega. Right, and the omega bar, we have to go all the way. It's not just it's the average of the two.
Yes.
Where the beat, so halfway in between the two originals, where the beat is really just half. Is it half the difference? Is that what it is?
The beat is half of the difference.
Half the difference, right?
Such that basically, that follows from this. I just want to make on page 108 in the book, this exact derivation is here, except they use delta omega over 2. So they use delta omega as the whole range. It doesn't. And then at the end, they call delta omega over 2 the beat frequency, which is a stupid thing. Why wouldn't you just call? Anyway, so I did it
and then I think
differently. But
he used the word modulates intensity.
yeah, that's just what.
Beat, that's the words he used. So
a beat. If you want to say like, what do you mean by a beat? You could say it's a fancy way to say it, but you could say it makes the intensity sort of a periodic function. It's just this function. Because the amplitude is periodic.
What was your question?
Yeah.
Ash?
Yeah. It's about quiz number 1. Did you look at that quiz at all?
No.
So, the first question is a work energy problem.
Okay.
If you want to look at
Yeah, sure.
part A, real quick. You can read it.
No points on, and then got all points.
Okay, so when you throw your sum of mass device straight down from a height of 1 meter with initial speed of 2, hits the floor, it deforms by 0.1 meters and stops without bouncing back. What is the average force on the floor? And if it's done straight up from the same height with the same initial speed. Okay.
So my question is, and I don't know if you'll be able to answer, but in class, that deformation
Yeah.
distance of 0.01,
Uh-huh.
we didn't account for that as a change in the potential energy.
Oh, okay.
And he marked most of people wrong because they didn't account for that,
Uh-huh.
are we supposed to account for that deformation changing our potential energy?
He gave us the points back because
Great, but I don't know what the, like, moving forward.
Well, so the thing is, from reading, wait, so you're saying that question you marked?
Mark
Wrong.
wrong, but then he gave us points back, like Ron said.
Okay, I don't actually agree with him because I agree with him giving the points back. I should just.
well, the total mass moves farther, so I think he's right. The
Oh,
mass-
I see.
But
Okay,
it
sorry.
basically meant-
You're right. You're right.
You can't.
The
Create
center of
a-
mass. I was thinking if he meant the floor dense, then okay, it does move down a little bit. But if the device dense,
And I think
but I guess
during
you're right that the mass is moving down.
The mass still went farther, so
Yes,
there's still
yes,
more.
yeah. Okay, fine. I agree with him. But
Yeah.
it's a little annoying. I mean, the point is that when he gives you numbers, so this is the thing. If he gives you questions with numbers, which I don't like, but because he's doing that, he has to allow some rounding. And I would look at a question like that and say, I don't need, it's a
It was-
rounding error off.
It was 5 newtons. It was 10%,
Really?
or 1%. Yep, it was 5
got a
newtons.
6 Newton difference.
Yeah.
But if let's say the floor does deform, does that mean I do have to take into account that change in that negative potential energy?
Yeah, both in both cases. So
in
if
both cases.
yeah, that was what I was just confused and you corrected me. But yeah, if you have like this is a device, phone or whatever, and you have the floor here. Here's the center of mass. This is what you're actually considering when you measure distances and stuff, right? I mean, really, I guess you would. Well, okay. When you talk about energy, you're talking about the center of mass. And so, if this hits the floor and dents the floor a little bit like that, of course, the center of mass is actually going down by that distance more. If the phone dents like that, it actually is the center of mass actually gets closer to the floor, also. So because the center of mass can get closer to the floor by that much, the total distance the center of mass travels is its initial height to its final height, which may be like a little below where it would be if it didn't dent anything. Yeah, so basically it's about the center of mass, what's the lowest position it reaches versus its initial position.
That was my question.
You do this one.
Yes. A yo-yo. It's a good start.
Just a yo-yo.
I feel like all the yo-yo problems have like some hitch that like completely changes it, and I always give on.
Thin ring of radius r and mass m. Right? Yeah. So therefore we know this is going to be mr squared because it's a ring. It's not a disk. Sorry. They draw. I was like, what is going on? They're asking what's happening, and they don't say anything, but they mean that there's a string there. And they tell you it goes that way, and then. Okay, so we want to Fibra diagram circle. Oh, equations of motion. The downward linear acceleration is a function of g, and the tension, and if it was a disk, which would reach the bottom first. Okay. So,
Thanks.
so for a three-body diagram, well, let's draw it. Okay, so there's two forces on this, right?
Mhm.
There's the gravitational force, which acts at the center of mass. It's a little weird because there isn't any, it's actually a ring. So there isn't any things at the center of mass. It's an empty space, but it still acts there. So that's just how it works. So this is mg, or you could write f of g if you want. It doesn't, you don't have to actually say what they are, but, big M. There's this mg, and then up here we have a force going up on the left side that must be just some kind of tension, right? So that should be the free body diagram. Okay, and now from basically immediately after you write the free body diagram, you should write the equations of motion. So what are the equations of motion? Well, we know that there's it is not fixed. I mean, we kind of know that. Well, we don't know for sure that it's not fixed. It could be. It's not fixed. They tell us it's not like there would have to be some other. They would have to tell you some piece of information. So it's not fixed. So therefore, the sum of the forces is going to be equal to the mass of the object times its acceleration, which is going to be equal to, well, it's going to be the, let's call downward positive. I know it sounds weird, but it'll be a little easier. So mg will be positive, and we have minus t because it's going up. So this is the linear equation of motion. We also have we have infinitely many angular equations of motion, but we can just pick one, of course. So then we take the sum of the torques. Now we have to pick a point. This doesn't mean anything by itself. We have to pick our actual point. So I guess the obvious pick would be to pick, well, I guess, no, you know what, it's not obvious. Let's pick the center as the torque point. We don't have to. We could pick this point. And I actually don't know for sure which is going to be easier. But let's pick the center as the torque point. Did you pick the center?
So I lost points for using the parallaxis theorem, so let's pick the center.
Okay.
You do both.
You could do both, but
You could do both. The thing is, they're going to be
points
redundant.
for doing the parallaxis theorem incorrectly.
Oh, okay.
Yeah.
Not just for doing it.
Yeah.
Okay.
Not just like
I was going to say this.
Goodness.
passive resistance kind of thing. It was just I did it wrong.
Right, okay. So the torque about the center, let's just write both. I'll put T for where T is. Well, this is going to be, actually, you know what? We should do the center because we only know I. Well, we could use the parallaxis theorem. Okay, let's do both. T around the center, the torque around the center, there's only one. And the radius we know is R. And it's going to be, I'll call this positive, I guess. So it'll be just T times R. Oops, T times R. That's it. There's no angle because they're all perpendicular. And then, of course, the torque due to the gravity at the center is 0 because the distance is 0. Now if we take the torque the torque at the point of tension, which is the edge there, what will be the torque? Well, it'll be T, again, it'll be mg, the force, times R. That's it, because R is the distance from the center, which is here now, to the point where the force is applied, which is a distance R away, and they're at right angles, right? Now, the key, though, is that this, if you wanted to use this, the equation of motion would just be I alpha, which would be mr squared. We know that that's mr squared times alpha, and we know that alpha is r alpha is a, right? Because we know that the r always goes with the Greek letter. That's a thing to remember. And so, because I always forget. And so alpha we can write as a over r. So this would actually just be mr. A. And this is tr, and so we can cancel this. We get t equals ma, I guess. We could also do it, now hopefully let's actually check that because it should be the same thing. The torque here is going to be equal to I alpha again, but it's not going to be I of, it's not going to be mr squared, it's going to be the rotation around here. So we can use the parallaxis theorem by saying I around t is going to be I around the center plus md squared, where d is the distance we moved the axis. So this would be mr squared plus m, and now d, what's d? Well, d is r, because we moved it a distance r. And so we get 2mr squared. So this would be 2mr squared times a over r for alpha. But this would be, sorry. Okay, no, that's right, that's fine. Is that right? Yeah.
Sorry, so the parallel axis same part is the A over R.
The parallel axis same part is the
Is that right?
no is
We
this
haven't done-
part.
Oh, it's over there.
Yeah.
Oh, got it.
Sorry, I changed that. Yeah. So it's 2 MR is the I around the edge.
For both of those, would the A be the acceleration of the center mass?
Yes, because alpha would be the angular. So alpha for the first one is just the angular acceleration around the center, which is related to the the linear acceleration. Well, sorry, it's real. Which is related because this is a string, right? So because this is a string, any angular acceleration corresponds just to linear motion, right? This alpha here is not that. It's the angular acceleration that the center does around this point, but that's actually the same exact thing.
Okay.
It's sort of a mirror image. So they're both happening. It's not always true. Like it wouldn't. It's actually sort of. This is very confusing sometimes. But in this case, they're actually the same thing. It would be this A is the linear acceleration of the center of mass.
And we would proceed with just one of these, right? We would either use
Yeah,
the torque around the center, or the some of the torque around, or I guess point T.
Right. Now I'm trying to see how. So these should have the same information in them. As in, there's 3 equations, and there should only be 2 that we need. So this would be mg r equals 2ma. So these are 3 equations of motion. Oh, and the m's cancel. So gr equals 2a. Okay. Now, so this
For that,
yeah.
where you're pointing right now,
this
should that actually be I equals? I mean, shouldn't that be MRA? Because alpha is A over R, and it's
Yes.
R squared.
yes. So alpha I changed to a. This is a.
Okay.
I changed. Yeah, it's hard to read probably, but this is alpha, and I changed to a over r, and I canceled one of the squares. And then there's an r over here. This is tr, which is the
What's that like right below it?
This
Oh,
one?
T equals MA.
t equals ma. Yeah.
Okay, sorry, I thought that was an I. Never mind.
No, it's right.
I just got confused. I thought.
Yeah.
So everything's an I except for.
These are t's.
Oh,
This-
TR
yeah.
equals MRA.
T. So this is this.
Oh, what is I?
Okay. Okay. Gotcha.
Yeah.
Thank you.
Sure.
Because they both are squared.
For the bottom, the MGR equals 2MA.
Uh-huh.
You,
So
I think
forget
you've
an R?
lost an R. Yeah. So
Oh,
if
yeah, you're right.
If you keep the other R, then you're going to have to add one to the other side. Yeah.
Right.
So the M's and the R's then cancel. It's G equals 2A.
Yeah. Seems too easy.
Yeah.
G.
You should know the choir
So
then.
half of G. Oh, I guess that's fine. So A is therefore G over 2.
Mhm.
Actually, all right. You know what? Let's check by using both of these. So if T, see, this is what I'm no. Well, okay, that's okay. Oh, yeah, okay, good. So if we plug, so we could have used these 2 equations. It's not. Oh, okay. Sorry, I'm confusing myself.
Where are we going?
The point is we have 3 equations of motion that we could do, but of course 2 of them we don't actually need the torque around every point. We could, that's totally fine, but it should give us the same information. So what this is saying is that if we only did these 2, we should still get the right answer. And let's do it. Well, if we plug in t equals 2a here, we have ma equals mg minus t equals, sorry, ma, not 2a. ma, we get 2ma equals mg, and this gives us a is g over 2. So that's the same as that, right? As that. So somehow it was actually, if we knew, I don't know how we know this, but if we knew to use this torque equation, we only needed one equation of motion to get the whole answer.
Right.
It just, because in this problem, there's like literally only one like variable, it's just a, right? The t is gonna, we don't care about t. We could solve for t if we want. We could just plug in a here and we get mg over 2.
And
Yeah.
the reason for the first equation we have force equals mg minus t.
Yes.
T is
Tension
negative
restraint.
because the yo-yo is going down, right?
You can make it up.
Okay.
I wanted to make a always be a positive number, just because what we care about is a, which is going down, right? So if we just call that positive, then t is going backwards.
Okay. Because
But
like
it's up to you.
sometimes he'll like take points
G
off for
over
that too.
two.
So
Uh,
So it is.
I know like for the first quiz, I kind of like messed up on
I
the
mean, so
directions.
if he specifies which direction to call positive, you should do that. Or if you call one thing positive and later switch it, you shouldn't do that. But if you just use the one convention, you should not take points off.
But in this case, you're thinking about it going down, which
Yeah.
is why it's positive.
Yeah. That you have to keep it consistent, though, of
Okay.
course. Yeah. So I would. Yeah. If you think that you made just a convention, you were consistent, and he takes points off, you should ask him because he's definitely even said in class that's of course everyone physics teacher should say that, but I've heard him say that you can pick any convention, it should be fine. So, but yeah, in this case, I just picked the only thing that was going up is t in the whole
Mhm.
problem. Everything else is going down. So you might as well just save yourself a lot of minus signs. But of course, if you would prefer, if you could make a rule, if you want, to just say every problem I'm always going to call up positive, you could just do that too. That would be probably a little bit easier to remember
Okay.
because you wouldn't have to think about it every time. But you could even draw,
So I
like
guess
that
if
on
you
the
did
problem.
the top one with a
Of
step,
course, that doesn't tell you about the
there's no
torque.
steps.
So you don't like. Does this mean that
If you
this
did the
is
one on the
positive
top
torque or
with the center,
this?
there's nothing
Like,
step.
because if you put
T equals-
like, one side's going up, one side's going down. So
Yeah.
so that you have to also make a convention
Okay.
and decide. Anyway.
Oh.
I called this torque positive because I knew that if it did this, it would actually go down because that's just how like a yo-yo would work. So I knew that if I called that positive, it would sort of match the same sign as I used above here. Okay, what was the last part of was it the whole thing? Oh, there was there's a thing.
What's
oh,
the tension?
the tension, right. So the tension we could just, now we have A, we could just plug back in m g over 2. So we just plug in any of our equations. Of course, we could also plug in here. That'd be fine too. Anything we have for A, for T, we could plug in. And notice it's very important that T does not equal, like the force upward does not equal the force downward. We obviously knew that when we made this equation, but it's just really important to know that it's actually specifically not equal. Of course, we know that it's not equal because otherwise there would be no acceleration. But it's very tempting to, when you do, 40 problems where the forces balance and net force is 0, and then you do a problem like this, it's very tempting to just say, oh yeah, net force is 0, but of course you have to put A as a variable. Okay, and then, so that's where the tension, and then they ask you if it was a disk, a solid disk,
Yeah.
which would hit the ground fast or whatever. So because there's no
Equal mass.
of equal masses, yeah. So it's, I mean the
All comes back to I.
right. The only difference is going to be I, and we could work through and just see what would the acceleration be if I was whatever it is for a disk, right? If it's larger, then of course that means it's gonna hit the ground sooner. If it's, well, we don't need to work out like a what do you call it, kinematics equation and see find the actual time and the ratio of the time and all that stuff. We don't really need to do any of that because if we know that the acceleration is gonna be constant, and if the constant acceleration is higher for object A than object B, then object A is going to hit the ground sooner, right? So if we wanted to change I to be, well, I prime, I'll say, is 1/2 mr squared. This is for a disk, right? So what would we have to change? This wouldn't change, of course. This would change. We would have a, now, really I would write this out separately, but I'm just going to do it like this. We would have 1/2 here, and 1/2 here, and 1/2 here. Okay? And then here, here, we would have a, this would be, okay, it would be, what was this 2 from? Oh, from the parallaxis theorem. Oh, right. So the parallaxis theorem would actually give us 3/2 mr squared, because here, center is 1/2. And then I'm not going to put all the primes in. But anyway, so we get a 3/2. So we have 3/2 here, and therefore instead of this 2, we would have 3/2, and we'd have a 3/2 A. And then when we plug this back in, this would be 2/3. So it'd be 2/3 of G instead of 1/2 of G. So if it was a solid disk, it would be a higher proportion of G. Then, now, why is that true? I don't know. Well, actually, okay, it's kind of true because, well, this isn't, I don't want to make it seem like your intuition are too good.
You didn't even ask us to like do all of it out. If you just explained like what I was and if it's lower, then
Oh.
we gave you credit.
Okay. I mean, yeah, because, okay, so an intuitive way is just to say that I is a measurement of like the resistance to turning. And so if it was easier to turn, that's what this lower I means. It's easier to turn, then it's going to fall a lot faster.
Well,
Literally what I wrote.
and
There you go.
and if it has a larger A.
Yeah, I just mean if you didn't want to solve for A again. Yeah, if you want to solve for A, this is sort of foolproof because it's literally A is bigger. But yeah, you could say that, okay, well, if it's a smaller I, then it's much easier to get it to start turning, and so it ends up going much faster.
Mhm.
And you can imagine why, well, it's a little bit hard to imagine, I guess. Well, you can kind of imagine that things are, if you put all the mass around the edge, right? So it's just a hoop with it's a sort of heavy hoop, right? Because it's not like a thin, like if it's the same mass as a disk, imagine like a heavy disk or whatever, and then a hoop that has the same mass. To get the hoop like this to start rotating, you have to make all of the mass move at the top speed, which is the speed of the edge, right? The edge is moving faster than anywhere else in a wheel, right? So if you want to get that to spin, that's actually a lot more sort of mass you have to speed up. Well, it's the same mass, but you have to make it go a lot faster. The disk, if it was filled in, some of it near the middle, you don't need to really speed up that much, right? Because it doesn't need to go as fast. So you can kind of imagine that the same mass you actually need. Turns out it's half as much, but you couldn't really figure that out. Okay. Does that kind of make sense? And actually, sorry. Oh, sorry. I just want one more quick thing. That the parallaxis theorem, which is this, that if you can interpret it the same way, as in, if you wanted to spin a disk, a certain amount. What if you wanted to spin a disk, but you wanted to spin it like at the end of a big rod? That's actually much harder because not only do you have to spin it, but you have to like move it all. Like you have to move it much faster, right? Even for the same angular speed, it's actually going farther. So therefore, you need more torque and all that stuff to move it. So that's why there's this extra term. The farther of a pole you put it on, it's going to be much harder to spin it because it has to go faster. Yeah. Sorry, were you?
I'll wait until you have.
I am done.
Oh, okay. Did you post the solutions to 10 and 11?
11 are posted. 10 is there was a solutions thing on there. So I didn't write any of the solutions, but the solutions that were on there, he just told me to put on. And 10 had a bunch of errors. So I took it down.
Okay.
So
There's a circular motion.
Yeah, that was on there too. I just put it up. I don't know.
Just for funsies.
Yeah. Actually, I'm not positive that 11 is.
Gonna be on
No, that the solutions for 11, the numbers. Sorry, when I specify, the numbers for all the things look. I don't know for sure. The actual equations look fine. For 10, the equations did not look great. So that's why I got very suspicious. Then I was like, this doesn't look right. And as far as I checked, which I checked 11, they looked right, but I'm not going to like guarantee it or anything. The numbers I'm talking about. The equations, again, as usual, the equations are right.
There's a note on Blackboard saying that there's an assignment 12. I'm guessing
Yes.
that's just.
I don't know what
We're
happened.
not gonna. Okay.
Yeah,
So
it's
there's-
there's a grade thing, like a
Okay, so
block in
there,
the
so
grade
there
for
is
it.
no assignment 12.
There is not.
I also was looking through the solutions. I haven't gone through all of them yet, but for solution number 1,
Mhm.
there was just like a complete mashup of questions that weren't even on the homework.
Yes, that's
Is that-
another.
Is that
Problem.
common for all the rest of the solutions? Or?
Some of them have. So this is kind of annoying. If he told me to write solutions, I would have done them, but he didn't. Anyway, it's sort of not running as well as I thought it would. But he said absolutely don't need to write solutions, and I said all right. And so then I realized like 3 weeks ago that a lot of them are either the wrong questions or something. Some of them have some of the wrong questions, but most of them, I believe, all of them are on there somewhere, unless someone. I think all the questions are on the somewhere, but they're sometimes in a different number, or they'll be like extra questions. But they should all match the book, so they're just extra questions if you want to look at. But they might be, and also there's 2 sets. There's one called, it's like Solutions Assignment 2, and there's one called Solutions 2 or whatever. So sometimes you might have to look at both because one of them has a more updated one.
Okay.
I should just write a bunch of solutions. I just don't have a lot of time. But I believe all of the questions you've had to do for homework are somewhere on there, and the equations in the solutions are correct.
Okay, so
If you think the number answer might be wrong, you can let me know, and I can double check and let you know what's right. I found a few, and I've taken the one off that I found it in, but
fair enough.
I know it's not an ideal situation. But
What's that called these days?
also, there's an error in the textbook, so there's only so far you can go. Anyway, also I would use the Khan Academy, as I've been saying, but the Khan Academy thing about the photoelectric effect and stuff has like problems and stuff for better in the textbook for this. Of course, the downside is that you don't know for sure that these are like the types of questions. Yes, I know, but
All right.
I think I heard a request for one more problem
sure.
this time. What was your preference? Can we do one of the like block on a
Yeah.
floor, pulley on the corner,
Yes.
block hanging from the pulley?
With friction?
Let's do it up.
Yep.
All right.
That's better.
Well, I'll just say, okay. Sorry, my muse and my. Have you done? I feel like did you do anything with this?
Not really.
Oh, okay. Yeah, because I was gonna say I feel like we kind of skipped that. The force of friction
I
is
feel like it's
proportional to the normal force.
like given.
Okay, you just get the force. Okay, so we'll just say that there's friction or something. Okay. So now let's draw a free body diagram for M1 and M2. So this is a situation, there's given some masses. As usual, I'm not going to say what the numbers are because then it's sort of less clear to see, I think. And so, well, of course, we have this is M1. I'll draw M2 here. And so for M1, we of course have gravity and normal force. Whatever, they're not going to contribute because it's not going to move in that direction. We should really label them though, Fg and Fn. They should cancel out. And then of course to the left, we're given that there's friction. If they just said there's friction on the surface, and they didn't say where it was, we still know it's to the left because in this picture, of course, this is going to go this way. So the friction must be opposing force. There's no way it's going to go the other way, so it's sort of not ambiguous. Sometimes it can be a little tricky to figure out, but in this case, it's pretty simple. So, and we know, of course, that there must be some force to the right given by the tension of this string or rope or whatever it is.
He's also thrown like the pulley has mass at us.
Ah, that's a good one.
So there's two different tensions.
Yes. T1 and T2, okay. So we have another free body diagram for the pulley. T1, T2, I guess I gave it away. This is the free body diagram for pulley. It has to have a mass, let's say, I'll say M3. I know it's kind of annoying. I usually would use lowercase for these and uppercase for that, but I don't want to change variables now. This is for M3. M2 has gravity, which is, I'll say it's actually M2G, of course, and then upward we have T2. Okay. Now, because we have three free body diagrams, each of them is moving in one dimension. That's important. That's basically always going to be the case. You can always break it down. We see that there's two dimensions here, and of course, really I should really say we have M3G gravity and a normal force. We're not going to use that. We're going to use one dimension here, which is the angular direction, right? One dimension here is going to be the x direction, one dimension here is going to be the y direction. We don't have to worry about what direction they are because each one is sort of its own little world. That's why I drew it in the box. So we know that for this one, the free body diagram is going to be what? The sum of the forces is going to be equal to M1A. A is the acceleration. Well, we're going to call this way positive because we know it's going to move that way. We might as well. It's also to the right. That kind of makes sense. So the thing is that means if we call the acceleration to the right positive, that means that M2 going downward is also positive because they're connected, right? So we have to also say in this picture it has to be positive. Otherwise, it's going to mess up things. So M1A is going to be equal to the sum of the forces, which is going to be T1 minus F friction. Now F friction is going to be a constant, so we don't think it like T is actually a variable that we might need to figure out and solve for and use and stuff. F of friction is just a number, so we're not, we don't have to solve for that or anything. It's usually given to us. Or I guess we could solve for it at the end, but everything else is going to be the same. The free body, the equation of motion for this is going to be M2A, which is downward is going to be equal to M2G minus T2. Now, of course, normally if there was massless pulley, so if the pulley had no mass and we didn't have this picture and we did the thing I was drawing at the beginning, we have these two equations of motion and we can relate them. There's two unknowns. There's A and there's T. It would just be the same T. And we could solve for them. That would actually be pretty simple. Of course, there's plenty of room for mistakes, but the actual conceptual idea of just adding these equations together, for example, we could solve for A, whatever. But now, because we have this, we have a third equation, which is going to be, now it's a torque equation. So we don't care about these things. We're going to do the torque around the center. Let's say it's a disk. So we have I is 1/2 M3 R squared, has a radius R. And now the sum of the torques is going to be I alpha, which is going to be, so this way is positive, right? Because if it turns to the right, if it turns clockwise, then it's going to move in the positive direction there. So we have T2 minus T1. Sorry, T1, these are R's. RT2 minus RT1 because they're distance R away from the center. And of course, let's make it a little simpler because we don't want I's, and alpha, those are extra variables we don't need. So we can write this as 1/2 M3 R squared. And I'll erase this to make it A over R, which cancels one of the R squareds. So I'll stop for a second because I've been going very fast. So this equation of motion, so let's say how many unknowns do we have? A is an unknown, T1, T2 is an unknown, those are both unknowns. R is fixed. Actually, we could cancel all the R's. That's actually really nice. So T2 minus T1 is 1/2 M3A. So this is 3 and 2 and 1. So we used the three free body diagrams. They each had like basically exactly 2 forces on them. We just added up the forces in the same sign convention and we set them equal to Ma or I alpha, which is just Newton's second law. Now, again, like I said, we have 3 unknowns, these 3, and we have 3 equations. That's the right number, so we could solve for them. And so what we can do is just say, okay, well, let's actually solve this for T2, let's say. So this is now just a bunch of algebra we have to do. So T2 is going to be equal to T1 plus 1/2 M3A. Okay, that's this. And now we have T2 in here. We could actually plug this in, so we get M2A equals M2G minus T2, so it'd be minus this quantity, T1 plus 1/2 M3A. Now it's obviously a little annoying because there's 3 masses in here. Again, masses are given, so they're not variables. We don't have to solve for them. So we have this. And now this equation here has, I'm debating taking out the friction. Well, I'll leave it in. This one has the same variable. So this one has 2 variables, A and T1. This one has A and T1. Now we've changed it to 2 equations with 2 variables. So we have M1A equals T1 minus FF. And now let's do the same thing again. We could solve for T1 in here. So we would just add friction on this side. So now this is equation for T1. This just only comes from this equation. And now we could plug in T1 here. We get M2A equals M2G minus parentheses, and this is a constant, plus M1A plus 1/2 M3A. Now we have one equation with one unknown, A. So we should put everything with A on the left side, everything without A on the right side. We could factor out an A, and we would get. Okay, so I don't have enough room, so I'm going to try to do this in my head. There's a very big chance it will not work. Is that right?
This is where it's like a 95% chance I screw this up on the
Yes, I know. This is the place where you screw up because there's way too many variables, but yes.
Why is the friction force being added by mass 1 acceleration?
Well, the friction force was, like you could consider, so that the net force on this, which is Ma, is given by just the sum of these 2 forces.
Okay,
They're
never
both
mind.
forces.
I-
Yeah.
Yep, never mind.
So these are all forces. This is a force, and these are masses. So it looks a little weird here because it looks out of place, but.
My reason to trying to rationalize is saying like, what are the things that are trying to make the system go? What are the things that are trying to keep it from growing?
Yes.
So M2 is trying to make us go, but it's being weakened by friction,
Yes.
and then all those masses have to move.
Right. Exactly. So you can consider it as right. All acceleration formulas that are divisions you can consider as like forces over inertias. Right. The forces are the only force that's making it go to positive is this one, M2G. So if M2 goes to 0, well, you have to keep in mind that friction would have to go to 0 too, but then it would all be thing to 0. It's going to the left by the force of friction, right? That's just slowing it down. And then what does it have to move? It has to move a bunch of mass. It has a bunch of inertia. Well, it has to move both of the masses, M1 and M2, but it only has to move M3, the pulley, by some fraction, which has to do with the moment of inertia. It's like, so it's 1/2 because it's a disk. If it was a hoop, if this was a hoop, everything in here would be the same except you just have a plus M3. It would just be like a whole other mass. Because essentially you are sort of moving a mass by the same amount if it's like all on the edge. Anyway, so that's A. That's it. And if they wanted you to find the tensions, the individual tensions, we could. We have three equations altogether. We could always just plug back in for A. And each of them, this one would be a little annoying because there's two. But if you plug in here to A, you should be able to just solve for T2. That should be it. If we did, we can do the thing with the limits. If we turn off means set to 0. If we turn off the pulley, set the mass of the pulley to 0, it should still work, right? It shouldn't stop anything. It should just move a little faster. Well, yes, if we see if M3 goes to 0, what happens? This goes away, and we just get the equation, which kind of looks actually like the equation for just a normal pulley without.
If you make mass 2 bigger, it goes faster.
It goes faster, exactly, because that's what's driving it. If you make mass 1 bigger, all it does is slow it down a little bit. It decreases the acceleration because it's just more mass it has to move. If you set mass 1 to be 0, then if you set mass 1 and mass 3 to be 0, meaning so there's no pulley, there's a massless pulley, and there's no mass over here, that's like if you just cut this, right? And if you cut this, then you'd see that these go to 0. Pretend there's no friction because there's no mass 1 anymore. You would see that M2 would cancel and you just get A equals G. You would just fall. It's just falling now. So that makes sense. Does that make sense?
Thank you for your help this year, Keegan. And
Yeah.
I
Seriously, thank you.
really appreciate you putting the movies online.
Yes.
Yeah.
The number of times that it's 10 o'clock at night and you're on fast forward rewind. Very helpful.
I try. They asked me if I want to put ads on them.
Yeah.
Maybe I'll do that.
We'll allow
Either
you to split the
you put
profits.
ads on or we have to tip you at the
Is that how this works?
One or the other.
I'll tell you what, if you want, we'll send your material out to the sponsors. We get a nice little commissioning fee though. If they're taking you up on
Yes.
it.